is nothing like your first lesson. There is nothing like your first lesson. It's one of the most exhilarating feelings you'll ever have in your life.
So what is flying all about? It's about art and science, imagination and invention. It's about challenge and adventure, determination and skill, exploration and discovery. Flying is about all these things and more. The flying experience is as unique as the many individuals who take up the challenge to pursue the dream of flight. You may be thinking about learning to fly for one or more of these reasons, or you may have an entirely different motivation. Whatever the reason, if you yearn to spread your wings and expand your horizons, this is your chance. You can learn to fly. Where do you begin?
As you begin your training, one of the first things you will become familiar with are the components of the airplane and how to use the different controls to make the airplane respond. When you sit in the cockpit of an airplane, you're actually sitting within the framework of the airplane. This framework is called the fuselage and is the attachment point for the other major components of the airplane. It also contains the passenger seating and baggage areas, as well as the cockpit. Within the cockpit are the flight controls and the instrument panel. Located on the panel are the flight instruments and engine gauges. The flight instruments are helpful for verifying your direction of flight, determining your airspeed, and indicating whether or not you're flying level, climbing, descending, making a turn, and your rate and coordination of turn. They also can show how fast you are climbing or descending, and your altitude. The engine gauges are important for monitoring engine performance. On most single-engine airplanes, the engine is mounted in the front of the fuselage. Aircraft engines are covered with a cowling, which streamlines the flow of air over the engine and directs the air around the cylinders for even cooling of the engine components. You control engine power by using a throttle located in the cockpit. The engine provides power to turn the propeller. In small airplanes, the engine and the propeller make up the power plant, which produces the force necessary to move the airplane through the air. This force is called thrust. The wings, working in conjunction with the power plant, not only produce the force called lift, which keeps the airplane in the air, but also contain the control surfaces which allow you to bank the airplane. These control surfaces are called ailerons and are located outboard on the trailing edge of the wings. When you rotate the control wheel to the right, the left aileron deflects downward, and the right aileron deflects upward. This moves the right wing down and the left wing up. The result is a bank to the right. How this is accomplished will be discussed in a later section. Attached to the aft end of the fuselage is the empennage, which contains the horizontal and vertical stabilizers. In addition to providing stability, the horizontal stabilizer contains the elevator. As the name suggests, the elevator controls the nose up or down movement of the airplane. This is called pitch attitude. The elevator is controlled by the forward and aft movement of the control wheel. When you apply aft pressure on the control wheel, the trailing edge of the elevator deflects upward, producing a down force on the tail of the airplane. This in turn causes the nose of the airplane to pitch up. Forward pressure on the control wheel has the opposite effect. The trailing edge of the elevator is deflected downward, which pushes the tail up, causing the nose to pitch down. The rudder is the movable surface attached to the vertical stabilizer. It is controlled through the use of pedals located on the floor of the cockpit. Applying rudder pressure swings the nose of the aircraft left or right in a yawing motion. Your speed during flight varies according to what you wish to accomplish. For example, during an approach to a landing, it is better to fly at a slower airspeed. The use of flaps located inboard on the trailing edge of the wings helps you maintain this airspeed during the descent. Flaps are retracted or extended by a switch mounted on the instrument panel. Since there are times when using all of the flaps would be too much, most general aviation airplanes have 3 or 4 flap settings. All airplanes are equipped with some form of landing gear. The most common type found on training airplanes is the tricycle gear, with 2 main wheels and a steerable nose wheel. Steering is accomplished by moving the rudder pedals in the direction of the desired turn. Other aircraft may be equipped with 2 main wheels forward and a tail wheel. This type of aircraft has conventional gear. It is often referred to as a tail dragger. Seaplanes may use a hull-type fuselage or be equipped with floats for water operations. Higher performance aircraft have retractable gear, which improves their performance by streamlining the air flowing around the aircraft. No matter what type of gear is used, they all must be capable of absorbing the loads imposed by repeated landings and by taxiing over uneven surfaces. Brakes are also an integral part of the landing gear. They are activated by pressing individual toe brakes located on the top portion of the rudder pedals. Each brake can be operated independently of the other to reduce the turning radius during ground operations. However, you should avoid using the brakes for primary directional control because most of your turning can be achieved with the nose wheel steering alone. The parking brake can then be set by engaging the hand lever in the cockpit. What you have just viewed in this section is a brief overview of the airplane and some of its components. Your textbook goes into greater detail on these subjects and covers additional items which were not covered in the video.
In this section, we'll take a look at the parts of the airplane that provide the thrust necessary to sustain flight. In addition, while gaining a basic understanding of how the power plant operates, you'll learn how you, as a pilot, can monitor and control the engine and propeller. In many ways, the engine in an airplane is similar to the engine in your car. Both produce mechanical energy through a cycle which occurs within the cylinders. There are 4 strokes to every cycle: intake, compression, power, and exhaust. The first part of the four-stroke cycle is the intake stroke. As the piston moves away from the cylinder head, the intake valve opens and a combustible fuel and air mixture is drawn into the cylinder. Next, the mixture is compressed as the intake valve closes and the piston moves back toward the cylinder head. When the compression stroke is almost complete, both spark plugs ignite the mixture. The combustion drives the piston away. This creates the power necessary to turn the crankshaft. Finally, the exhaust valve opens and the burned gases are forced out of the cylinder. In light training aircraft, this cycle repeats itself approximately 1,300 times a minute during cruise flight. The same cycle is taking place in each of the other cylinders. However, the sequence is staggered, so a power stroke is always being applied to the crankshaft. This provides you with a smooth-running engine. Since the crankshaft is connected to the propeller, its rotation causes the propeller to spin and produce thrust. The cylinders on an air-cooled engine are cast with thin fins, which increase the surface area. Heat from the cylinders passes into these fins and is carried away by the airflow around the engine. Now that you have a basic understanding of the engine, let's take a look at the various systems that help you monitor and control it. Let's begin by taking a look at how the engine receives the spark necessary to ignite the fuel and air mixture in the cylinders. The basic source of current is a magneto, which produces a hotter spark at higher engine speeds than does the battery system used in your car. The magneto fires as soon as you engage the starter and will continue to fire as long as the crankshaft is turning. There are actually 2 magnetos for each engine, which means the airplane has a dual ignition system. Since the 2 magnetos are independent of one another, each one fires a different spark plug in each cylinder. This makes it possible for the engine to run on either set, so that your engine will continue to run safely if one magneto or spark plug fails. Besides being a safety factor, having 2 spark plugs in each cylinder improves the combustion of the fuel and air mixture, resulting in more engine power. The airplane's ignition switch controls which magneto you're using. For example, after the engine starts, normal flight conditions require the use of both magnetos. Before you take off, however, you can test the independent performance of each side. Just how you perform this check will be discussed in the pre-takeoff checklist section of takeoffs and landings. When shutting down the engine, it's very important that you remember to turn the ignition switch off. If it is left in the right, left, or both position, the engine could still start if someone moves the propeller from outside the airplane. Turning off the master electrical switch without turning the magnetos off will not prevent the engine from starting, because the magnetos are separate from the rest of the aircraft's electrical system. To achieve the best performance from your engine, each cylinder must receive the proper fuel-air mixture. The engine induction system lets you regulate the proper mixture required during different flight conditions. Before the mixture enters the cylinder, a carburetor meters the correct amount of fuel and then combines it with filtered air. The carburetor, however, is calibrated to provide the proper fuel-to-air combination at sea level when the mixture control lever is set in the full rich position. But as you have learned, the density of the air decreases as you climb to higher altitudes. Subsequently, the density of the air entering the carburetor will decrease, while that of the fuel remains the same. This means that the mixture becomes too rich, or there is too much fuel for the density of the air entering the carburetor. A mixture control lever or knob is located in the cockpit. It enables you to adjust the amount of fuel to maintain the correct fuel and air blend at varying altitudes. If you fail to adequately lean the mixture as recommended in the pilot's operating handbook, the engine will run rough. An overly rich mixture causes a cooling effect in the cylinders, and this can foul spark plugs and valves, resulting in a loss of power. On the other hand, if you lean the mixture too much, the engine temperature will become very hot. A mixture that's too lean can cause detonation and/or pre-ignition, which can damage or even destroy major components of the engine. Detonation is the explosive combustion of fuel in the combustion chamber, rather than the smooth burning that normally occurs. It can develop whenever you allow the engine to overheat. Besides occurring with an excessively lean mixture, it can also result from using an improper fuel grade. Other causes include taking off when the engine is near maximum allowable operating temperature, and flying with a high power setting and low airspeed configuration, which may not provide adequate engine cooling. A different form of abnormal combustion, pre-ignition, is caused by a hot spot in the cylinder and occurs when the fuel and air mixture ignites prematurely. This hot spot may be a carbon deposit on a spark plug or any damage found around the combustion chamber. Another potential source of engine roughness and possible fuel starvation is carburetor icing. Because of the rapid cooling that takes place inside the carburetor when fuel vaporizes and the air expands, moisture can condense, freeze, and begin adhering to the internal surfaces. This accumulation of ice can substantially restrict or even cut off the fuel-air mixture to the engine. Although carburetor icing can occur over a wide range of conditions, it is most likely to form when the relative humidity is above 80% and the temperature is below 21 degrees Celsius or 70 degrees Fahrenheit. In most training airplanes with a fixed pitch propeller, the first indication of carburetor ice and the subsequent power loss is a gradual decrease in engine RPM, which may not be readily noticeable. If this situation occurs, you should apply carburetor heat. This routes heated air into the carburetor to melt the ice. On some of the airplanes that you'll fly, a fuel injection system is used instead of a carburetor as a more precise way to meter the fuel and distribute the fuel-air mixture to the cylinders. Although fuel injection is typically a more expensive type of induction system, it has several advantages over a carburetor. These include a more even fuel distribution to the cylinders, which reduces operating temperatures, improved acceleration, and lower fuel consumption. The system is also less susceptible to induction icing. Although fuel injection has many benefits, you may experience some problems with the system, particularly when attempting to start a hot engine. The problems occur after shutting down the engine as the air temperature inside the tightly enclosed cowling increases. The temperature inside the induction system can reach a point where the fuel vaporizes, creating a vapor lock, which effectively blocks the fuel flow. Although the specific starting procedure varies, an auxiliary fuel pump is normally used to clear the fuel vapor and reestablish the fuel flow. Fuel vaporization can also occur during ground operations due to inadequate engine cooling, and you might have to use the fuel pump intermittently to purge the vapor lock and prevent fuel starvation. Whether you fly airplanes with a carburetor or fuel injection, engine efficiency decreases as you gain altitude, and thus the density of the air entering the engine is reduced. To overcome this drawback, some engines incorporate a turbocharger that compresses the air that enters the combustion chamber. This increases the density of the air. Ultimately, the airplane is capable of operating at higher altitudes, since the engine can continue producing sea-level power as you climb. During your pre-flight check, you should make sure the oil level is correct, because after the engine is running, the moving parts are lubricated by engine oil. This oil also helps to keep the internal temperature of the engine within acceptable limits. The heart of the oil system is the pump, which draws oil from the sump, pumps it through an oil filter and cooler, and then routes it to the engine. Gauges on the instrument panel display the oil pressure and temperature. A green region normally shows the correct oil pressure. If you observe an abnormal indication, you should assume that the engine parts are not receiving adequate lubrication. An oil temperature gauge lets you keep an eye on the system by displaying whether or not the temperature is in the permissible range. On many light airplanes, this gauge is the only indication of engine temperature. If the engine is running a little hot, you can assist in the cooling process by using a richer mixture setting, reducing your rate of climb, increasing airspeed, and reducing the power setting. The second part of the power plant is the propeller, which produces the thrust necessary to move the airplane through the air. The propeller consists of a hub and 2 or more blades. Since each blade is an airfoil, it is subject to the same aerodynamic factors that apply to any airfoil. The camber of a rotating propeller creates a lower pressure area in front of the blades, just like a wing creates a lower pressure area above the airfoil. This produces the horizontal lift or thrust necessary to propel the airplane through the air. However, unlike the wing, which is traveling at a uniform rate in straight and level flight, the tips of a propeller are traveling through the air faster than the area near the hub. Therefore, a propeller blade is twisted with less angle near the tips. This creates uniform thrust along most of its length. The overall angle of the blade determines its operating efficiency in various phases of flight. A propeller with a low blade angle is capable of producing more RPMs and is best suited for takeoffs and climbs. A blade with a high angle, however, is more efficient for cruise flight. Most light training airplanes use a fixed pitch propeller with an overall blade angle somewhere between a true climb propeller and one designed just for cruise. This provides relatively efficient thrust throughout the airplane's operating range. With a fixed pitch propeller, the blade's angle cannot be changed. On airplanes with a fixed pitch prop, you control engine power and propeller RPM solely through the use of a throttle. As you add power, the increase in engine and propeller RPM is indicated on the tachometer. Some airplanes use a more expensive constant speed propeller. With this type of prop, you can vary the pitch to obtain the most efficient blade angle during the different phases of flight. Airplanes with constant speed propellers have 2 power controls, the throttle and propeller control. As you adjust the throttle, the changing power output is indicated on a manifold pressure gauge. Manifold pressure is measured in inches of mercury and represents the pressure of the fuel and air mixture inside the engine's intake manifold. The higher the pressure, the greater the engine power being produced. By advancing the throttle, you increase the fuel and airflow to the combustion chamber and thus increase the manifold pressure. Since manifold pressure is measured in inches of mercury, the gauge is essentially an aneroid barometer. This means that when the engine is not running, the atmospheric pressure is displayed. The propeller control lets you change the pitch of the propeller blades, which regulates the RPMs shown on the tachometer. Your ability to select and maintain various blade angles and RPM settings for different phases of flight is where the efficiency of a constant speed propeller is measured. Changing propeller RPMs is much like changing the gears on an automobile or bicycle, where a low gear is best during acceleration and a high gear for cruise. For instance, before takeoff, you adjust the knob to set the propeller to a low blade angle. This provides high RPMs for maximum takeoff thrust. Upon reaching cruising altitude, you adjust the blades to a higher pitch. This produces a lower RPM and provides adequate thrust for cruising airspeed. Once you've selected the appropriate RPM, the propeller's pitch will adjust slightly during varying flight conditions so that the propeller load matches engine torque and the tachometer setting remains constant. Also, as you alter the manifold pressure with the throttle, the propeller will automatically adjust its pitch to maintain the selected RPM setting. Because the propeller can be very dangerous, exercise extreme caution when you're near an airplane. Even if the propeller isn't turning, the pilot in the airplane might be getting ready to start the engine. In addition, if you are flying with passengers, you should routinely brief them about the proper procedures to follow when around an airplane. The power plant installed in today's airplane is very reliable, but to get maximum use and consistent performance, you need to operate it in accordance with the procedures and specifications prescribed in the Pilot's Operating Handbook. Now that you have an understanding of how the power plant performs, let's take a look at how the engine is provided with fuel and examine the electrical system found on most training airplanes. Let's start with the fuel system. Generally, there are two types of fuel systems which you might encounter during your training. The first is the gravity feed type commonly found in high-wing airplanes. With this type of system, the fuel tanks are usually mounted inside the wings. Because of the difference in height between the tanks and the engine, gravity forces the fuel to the carburetor. A second type of system must be incorporated on low-wing airplanes, where the fuel tanks are positioned below the engine. Here, an engine-driven fuel pump supplies fuel from the tanks to the carburetor. However, this pump only supplies fuel once the engine is running. For starting, an electric boost pump is used to supply fuel. It can also be used as a backup should the engine-driven pump malfunction. No matter which type of fuel system your airplane uses, you must determine before each flight that your airplane has been filled with the proper amount of fuel. Always verify that the tanks contain the corresponding amount of fuel that was shown on the gauges. Never rely on the fuel gauges as your sole source of determining fuel quantity. You should also ensure that the tanks contain the correct type of fuel. Airplane engines are not all alike, and each one is designed to use a particular grade of fuel. To help with identification, colored dyes are added to each type. For example, 80 grade fuel is colored red, 100 low lead is blue, 100 is dyed green, and turbine fuel is colorless. The POH lists the acceptable fuel for the aircraft you're flying. If the proper fuel is not available, using the next higher grade of fuel for a short period of time is not considered harmful, as long as the manufacturer has authorized it. However, you should never use a lower grade because it can produce excessively high engine temperatures and cause serious engine damage. In addition, you should never use turbine or jet fuel in a reciprocating engine. Another consideration during pre-flight is to check for fuel contamination. You can do this by checking the wing tank drains and the fuel strainer. If you discover water or sediment, you should continue to drain the system to eliminate all traces of the contamination. One way to minimize water in the tanks is to make sure they are filled after the last flight. This helps prevent water vapor from condensing in a partially filled tank due to temperature changes during the night. Managing fuel consumption during your flight is equally as important as checking it before you take off. The fuel quantity gauges display the volume remaining in each tank. Besides showing the number of gallons, many also indicate the fuel's weight. To help you manage the fuel use efficiently, a selector valve is placed in the cabin, allowing you to select fuel from various tanks. While many airplanes have a selector valve that allows you to draw fuel from both tanks during normal operations, others necessitate switching back and forth from one tank to another. With this type of system, you need to avoid running on only one tank for an extended period of time, since the unbalanced fuel load will affect the airplane's stability. It's also essential that you follow the procedures outlined in the airplane's POH for changing tanks to ensure an efficient and uninterrupted fuel flow to the engine. Now let's turn our attention to how the airplane's electrical system provides the power to run the avionics and electrical equipment. Most modern airplanes derive electrical energy from an engine-driven alternator, which produces alternating current and converts it to direct current. The direct current is then delivered to a bus bar, which distributes the power to the various electrical equipment. This typically includes, among other things, various lights, the radios, the turn coordinator, and gauges. Another critical component in the electrical system is the battery. Although its primary purpose is providing a means of starting the engine, it also can be used in an emergency to provide limited power to the electrical components. An ammeter mounted on the instrument panel measures the amount of current flowing to or from the battery. It provides you with the means of monitoring the electrical system. After the engine starts, the needle will deflect to the plus side to show that the battery power lost during the start is being replaced. Once the battery is charged, the needle will stabilize near zero to show you that the alternator is now supplying the current to the electrical system. If the needle begins pointing to the minus side, it means that the electrical load is exceeding the alternator's output capability and that the battery is helping to supply electrical power. A negative indication could also mean a malfunctioning alternator. If this occurs, you should reduce the electrical load by turning off non-essential equipment and land as soon as practical. The entire electrical system is controlled with a master switch. This switch is designed in such a way that the battery function can be activated without the alternator. But the alternator half cannot be activated independently. If you experience an alternator problem during flight, you can remove it from the electrical system by turning the alternator side of the switch off. Just remember that when doing so, you place the entire electrical load on the battery. In order to protect the various components from the possibility of an electrical overload, your airplane is equipped with fuses or circuit breakers. Normally, each component's name is printed on the circuit breaker panel. If an overload occurs, the circuit breaker will pop, protecting the various components within that circuit. After a short cooling period, you can reset the breaker by pushing it back in. However, if it pops again, an electrical problem probably exists, and the device should not be used until it is repaired. As with all of the airplane systems, a sound knowledge of how the fuel and electrical systems operate will help you to become a safer and more professional pilot. The aircraft POH will not only provide you with an abundance of information for normal operations, but will also detail the appropriate actions to take in the event of a system malfunction.
There are 6 basic flight instruments which are designed to provide you with the information you will need to control the airplane. Let's begin by looking at the pitot-static instruments. The pitot-static instruments include the airspeed indicator, altimeter, and vertical speed indicator. Because these instruments operate on the principle of pressure differential, you need to understand how the atmospheric pressure surrounding your airplane changes in various situations. For example, as you climb to a higher altitude, the density of air decreases. Therefore, the pressure of the air is lower. The pitot-static instruments are able to sense the changes in atmospheric pressure and provide you with information concerning your airspeed, altitude, and rate of altitude change. During flight, the pressure surrounding the airplane enters the instruments through a static port, which is positioned in an area of relatively undisturbed air, such as the side of the fuselage. At the same time, ram air pressure enters through a small hole at the front of a pitot tube, which is mounted so it is exposed to the relative wind. While all three instruments use the ambient air pressure provided by the static port, only the airspeed indicator uses ram air pressure from the pitot tube. The airspeed indicator displays the speed of your airplane through the air by measuring the difference between the ram air pressure entering the pitot tube and the ambient air pressure that enters the static port. As this pressure differential changes, the airspeed needle moves. A number of color-coded arcs are incorporated on the instrument face and represent various airspeed limitations. For example, the white arc shows the flap operating range. The upper end of the white arc indicates the maximum airspeed permissible with flaps fully extended, while the lower end shows the stall speed with full flaps. The white arc becomes very useful during the landing phase of your flight because it helps you determine when you can safely extend the flaps. It also shows you when you're approaching the normal stall speed in the landing configuration. Most of your flying, however, will occur at airspeeds within the green arc, which is known as the normal operating range. The lower boundary of this arc shows the airplane's stall speed when it's at the maximum takeoff weight with the flaps up, and, if applicable, the landing gear retracted. The upper limit of the green arc is the maximum structural cruising speed. You can exceed this airspeed and begin flying in the yellow range only when the air is smooth and only with caution. Finally, a red marking is placed at the never exceed speed. You should never operate above this speed because structural damage could occur. During your flying, you will become familiar with several types of speed. For example, indicated airspeed is read directly from the instrument. However, when calculating airplane performance, you should use calibrated airspeed, which is indicated airspeed corrected for instrument and installation errors. You can determine calibrated airspeed by referring to the table provided in the pilot's operating handbook. True airspeed is your actual speed through the air. It is calibrated airspeed corrected for density changes due to altitude and non-standard temperatures. Another term, ground speed, describes your actual speed over the surface. In a no-wind situation, true airspeed, or TAS, and ground speed, GS, are equal. A headwind, however, will decrease your ground speed. Conversely, a tailwind will increase it. Now let's look at how the altimeter works to provide you with altitude information. The altimeter senses pressure changes in the surrounding atmosphere and converts this information to a display of your altitude. Most altimeters have 3 pointers. The longest shows hundreds of feet, the middle-sized pointer, thousands of feet, and the shortest one shows tens of thousands of feet. To properly read an altimeter, you must first look at the shortest pointer. In this case, it's between 0 and 1, indicating you're below 10,000 feet. The middle pointer shows that you're somewhere between 5,000 and 6,000 feet. And the longest pointer shows you're halfway between 700 and 800 feet. Putting the 3 together, you come up with an altitude of 5,750 feet. Be very careful when reading an altimeter because misreading it could lead to serious consequences. The altimeter also has a barometric scale which can be adjusted to compensate for variations in atmospheric pressure. Here you can see the numbers 29.9 and 30.0. You read these by adding a 0 to each number to get 29.90 and 30.00 inches of mercury. The barometric setting on this altimeter is read as 29.95 since the pointer is halfway between 29.9 and 30.0. As you can see, the distance between the printed numbers represents 1/10 of an inch of mercury. Since the barometric pressure changes approximately 1/10 of an inch for every 100-foot change in altitude, moving the scale 1/10 of an inch will cause the pointers to move 100 feet. Altimeter settings are provided by FAA facilities such as control towers and flight service stations. Before every flight, you should adjust the altimeter to the current reported setting. If you set it correctly, your altimeter should read the field elevation. Then during your flight, especially if you're leaving the local area, you should periodically adjust the altimeter to the latest reported setting. Let's see what might happen if you fail to make these adjustments. Suppose you're maintaining an altitude of 5,500 feet, and you're flying into an area of lower pressure. The altimeter interprets the decreasing pressure entering the static port as a climb, although you're actually flying level. When you notice the altitude gain, you will naturally lower the nose to descend to your desired altitude. However, in this situation, you will actually be descending to a lower altitude, even though the altimeter shows a return to 5,500 feet. To a certain degree, this same situation occurs when you're flying from an area of warmer air to one with cooler air. Obviously, this could be dangerous if you're flying over obstacles or high-rising terrain. It could also place you far off your appropriate VFR cruising altitude. A helpful memory aid to assist you in determining whether you're higher or lower than before is the phrase, "When flying from high to low or hot to cold, look out below." This means that in these situations, you're going to be below the altitude indicated on your altimeter. The best way to minimize this type of error is to periodically reset your altimeter to the current setting as reported by the nearest FAA facility. Keep in mind that an altimeter measures altitude above a specific reference. There are various types of altitudes depending on which reference you are using. For example, indicated altitude is read directly from the instrument. If the proper barometric pressure is set in the altimeter, its indication will be based on a standard plane called mean sea level, or MSL. In other words, if your altimeter is reading 2,000 feet MSL, you are actually flying 2,000 feet above this standard sea level reference. The distance between your airplane and sea level is called true altitude. If you're flying over a surface higher than mean sea level, you must subtract its height from the altimeter reading to obtain your distance above the surface. This difference is called absolute altitude and is often referred to as height above ground level, or AGL. Pressure altitude is referenced to a standard level of 29.92 inches of mercury. It is used with the existing temperature to determine density altitude. Density altitude is pressure altitude corrected for non-standard temperature. It is not really an altitude, but is a theoretical value used in the computation of aircraft performance. Now let's take a look at the last pitot-static instrument, the vertical speed indicator. Like the altimeter, it is connected only to the static port. As you climb or descend, the VSI measures how fast the ambient pressure is changing and displays the rate of altitude change in feet per minute. In this situation, you're descending at 300 feet per minute. One of the most valuable uses of the VSI is that it immediately provides you with trend information when you begin to gain or lose altitude. After a few seconds, the VSI stabilizes and displays the actual rate of altitude change. Although the pitot-static instruments provide you with essential flight information, you need to use them in conjunction with the other instruments to precisely control your airplane. Gyroscopic instruments give you information about your airplane's attitude, its rate of turn, and its heading. These instruments include the attitude indicator, the turn coordinator, and the heading indicator. Before we take a look at the information these instruments provide, you need to understand how they operate. The primary element of each gyroscopic instrument is a heavily constructed spinning gyro mounted in gimbals. If the gyro is freely or universally mounted, it will remain in a fixed position no matter where you move its base. This degree of stability is known as rigidity in space. If the gyro is mounted in an instrument so the airplane can rotate about it, the aircraft's movements will be displayed on the instrument face. Most small airplanes use two different sources of power to spin the gyros. Typically, the turn coordinator uses electrical power, while the attitude indicator and heading indicator are driven by a vacuum system. By using two independent sources of power, you will still have some degree of backup should one system fail. A vacuum or suction gauge is normally positioned on the instrument panel to allow you to monitor the vacuum pressure. If the pressure is not at an adequate level, the gyro instruments could be unreliable. Now let's take a closer look at the attitude indicator. This instrument senses rolling and pitching movements, providing you with a pictorial view of your airplane's attitude in relation to the natural horizon. The attitude indicator uses a miniature airplane and an artificial horizon to show both angle of bank and pitch. The artificial horizon is controlled by the spinning gyro. Index markings are incorporated to show you precisely how much pitch and bank you're using. An adjustment knob enables you to align the miniature airplane with the horizon bar before takeoff and during straight and level flight. As you enter a level left turn from straight and level flight, the attitude indicator will detect and display the change in bank. In this situation, you are maintaining 30 degrees of bank. As you roll back to wings level, the attitude indicator will give you the same indication as the actual horizon. When you enter a descent from straight and level by lowering the nose, the instrument again displays your position in relation to the actual horizon. A combination of pitch and bank is shown just as easily. For example, during a climbing right turn, the nose is above the horizon, and the miniature airplane is banked to the right. Now let's take a close look at the information displayed by the electrically driven turn coordinator. The turn coordinator is actually two separate instruments. One instrument contains a spinning gyro which senses rolling and yawing movement. A miniature airplane on the face of the instrument represents the actual airplane and indicates your turn rate. For example, as you roll into a right turn, the miniature airplane will bank in the same direction, showing you how fast you rolled into the turn. Once the turn is established, it indicates how fast you're making the turn. It does not, however, show your actual bank angle. During certain maneuvers, you will be required to perform a standard rate turn, which is a turn rate of 3 degrees per second. This means that you'll be turning 180 degrees in 1 minute, or making a complete 360-degree turn in 2 minutes. When the miniature airplane's wing is aligned with the lower index mark, you're in a standard rate turn. The second part of the turn coordinator is the inclinometer, commonly referred to as the ball. It consists of a curved glass tube containing a ball that moves in response to gravity and turning forces. The ball is used to establish and maintain coordinated flight. For example, during straight and level coordinated flight, the force of gravity causes the ball to settle in the lowest part of the tube. During a coordinated turn, the ball will still remain centered between the reference lines. However, if the bank becomes too steep for the turn rate, the ball will move to the inside of the turn and indicate a slip. If the bank is too shallow for the turn rate, the ball will move to the outside of the turn, indicating the airplane is in a skid. You can center the ball by varying your angle of bank, or by applying rudder pressure in the direction of the deflected ball. To help you determine which rudder pedal to press, use the saying, "Step on the ball." In other words, if the ball is out to the right, step on the right rudder pedal. The final gyroscopic instrument is the heading indicator, sometimes referred to as the directional gyro. Like the attitude indicator, it receives its power from the vacuum system. The heading indicator is a relatively simple instrument to read. The graduations on the face are spaced at 5-degree intervals, with the cardinal headings north, east, south, and west marked with a letter. Between the cardinal headings, each 30-degree increment is marked by a number with the last zero omitted. This instrument is showing a northwesterly heading of 330 degrees. Because the heading indicator does not have a magnetic north-seeking element, you will have to set it prior to each flight. You will also need to reset it during flight to counteract gyroscopic precession. The instrument to use when resetting the heading indicator is the magnetic compass. Since it is not a gyroscopic instrument, it will not experience the same errors which occur in a heading indicator. In addition, because it doesn't require any power, it is an important backup source for heading information. However, a magnetic compass does have its own limitations, which you should be familiar with when using it for directional information. For example, when a compass is mounted in an airplane, metals and electrical equipment produce local magnetic disturbances, resulting in a slight error in the indication. This error is called deviation. A correction card is mounted near the compass so you can correct for any deviation. For example, in this airplane, if you want to fly a magnetic heading of 090, you'll need to fly a compass heading of 088 degrees. The compass is also affected by magnetic dip, which is the tendency of a compass to point down and toward the magnetic poles. This error is greatest when you're near the poles. As a result of magnetic dip, your compass will give an incorrect reading when you turn, accelerate, or decelerate. In the northern hemisphere, a turn from a northerly heading results in the compass initially indicating a turn in the opposite direction, then lagging behind the actual heading. This lag decreases as you approach an easterly or westerly heading. In a turn from south, the compass will indicate the proper turn, but will lead the actual heading. As in a turn from north, this error diminishes as the turn approaches east or west. Errors also occur when you're accelerating or decelerating, especially if you're flying on an east or west heading. When you accelerate, the compass will indicate a turn to the north, even though you're still flying straight and level. The opposite is true when decelerating. In this case, the indication will be toward the south. A simple memory aid to help you remember which way the compass will move is ANDS, which stands for accelerate north, decelerate south. When you use the magnetic compass to reset the heading indicator, remember these limitations and reset it only when you're flying in straight and level, unaccelerated flight. Once you've achieved the ability to use and interpret the flight instruments correctly, you should be able to control your airplane with more precision. This will make your flying easier and make you a more proficient pilot.
Have you ever wondered what makes an airplane fly? There are 4 forces acting on an airplane in flight. These forces are lift, weight, thrust, and drag. The study of these forces and their role in flight is known as aerodynamics. Let's take a look at how these forces work together to achieve straight and level, unaccelerated flight. This means that the airplane is not turning, climbing, descending, or changing airspeed. It should be fairly clear that before an airplane can fly, lift must be created. Lift is the upward force created by the effective airflow as it passes over and under the wing. Weight is the force that opposes lift and is caused by the downward pull of gravity. Thrust, created by the power plant, propels the airplane forward through the air, while drag, a retarding force, opposes thrust and limits the speed of the airplane. In unaccelerated flight, where thrust and drag are equal, the airplane will not speed up or slow down. Like thrust and drag, when lift and weight are equal, the airplane will not climb or descend. To help you understand lift, let's take a look at the basic principles of motion. In the 18th century, Daniel Bernoulli expanded on Sir Isaac Newton's laws of force and motion to describe the principle of airflow pressure differential. Observing what happened to air as it passed through a tube, Bernoulli discovered that as the velocity of a fluid or gas increases, its pressure decreases. He also found that with a constant velocity, the pressure of the air remains the same at both ends of the tube. If a constriction is placed in the middle of the tube, the same amount of air has to pass through a smaller area. This increases the velocity and decreases the pressure. If you were to replace the constriction with an airfoil, such as a wing, the same principle would still apply. As oncoming air meets the leading edge of the airfoil, it separates with part of the airflow going over the top and part going below. Since the air flowing over the top has farther to go, it must travel faster. The result is lower air pressure above the wing. This is a component of total lift. The remaining lift is provided by the downward-backward flow of air generated from the top surface of the wing. The lift provided by this flow can be explained by Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. The reaction to this downwash results in an upward force on the wing and an increase in total lift. Before we look at various airfoils and how they are configured to take advantage of the laws of motion and principles of lift, let's look at some of the terminology. A line drawn from the leading edge to the trailing edge of an airfoil is referred to as the chord line. The camber of an airfoil is the curve of its surface. On general aviation training aircraft, the upper camber is usually more pronounced than the lower camber. Any object moving through the air encounters a relative wind. This wind is always parallel to and opposite the flight path. The angle formed between the relative wind and the chord line is called the angle of attack. A way to measure lift as it relates to angle of attack is the mathematical expression coefficient of lift, or CL, which is determined by wind tunnel tests and is based on the design of the airfoil. Each airplane has an angle of attack where maximum lift occurs. This point is known as CL max. Beyond this point, the airflow begins to separate from the wing surface, becoming so turbulent that the airfoil can no longer create lift. At this point, the wing is in a stalled condition. The amount of lift that a wing can produce depends on several factors. One of these factors is wing design, which includes the shape or plan form of the wing. A straight wing has good slow flight characteristics, but is not structurally efficient in terms of lift and drag. A swept back or delta wing is much better at higher speeds. The tapered wing, on the other hand, has good slow flight characteristics and has a relatively efficient design. Another wing design factor is the aspect ratio, or the relationship between the wing's length and width. The aspect ratio can be found by dividing the wingspan by the average chord. In this example, the wing has an aspect ratio of 9. At a given angle of attack, the larger the aspect ratio, the less drag produced for the same amount of lift. General aviation training aircraft, for instance, normally have aspect ratios of 7 to 9, while gliders are usually between 20 and 30. Another design factor that affects a wing's flight characteristics is the angle of incidence. In this case, the wing is attached to the fuselage with the chord line inclined upward at a slight angle. You, as a pilot, can control lift by changing individually or in combination the airplane's airspeed, its angle of attack, and the wing configuration, such as lowering the flaps. If all other factors remain constant, doubling an airplane's airspeed develops 4 times more lift. This increase, however, is not without its drawbacks, since any increase in lift also results in an increase in drag. In addition, with all other factors remaining constant, an increase in angle of attack increases lift. For lift to remain constant, airspeed and angle of attack must be used in conjunction with each other. If airspeed increases, you must decrease angle of attack. Conversely, if you want to maintain the same amount of lift at a slower airspeed, you must increase the angle of attack. Another way of controlling lift is by changing the configuration of the wing. Lowering the flaps can increase the lifting efficiency of the wing and decrease the airspeed at which the airplane stalls. As flaps extend, they change both the camber and the chord line of the wing in the area of the flaps. This not only produces lower pressure above the wing due to the change of camber, but it also changes the wing's angle of attack. Suppose that with the flaps up, the angle of attack is 5 degrees. By lowering the flaps, which changes the chord line, the angle of attack increases to 10 degrees. This higher angle of attack provides more lift and more drag. Weight, like lift, is not a constant. It varies with the equipment installed in the airplane, the number of passengers, the amount of cargo, and the fuel load. During the course of a flight, the total weight of the airplane will decrease as fuel is consumed. In some specialized flight operations, such as crop dusting, firefighting, or skydiving, an additional reduction of total weight will occur. The forward-acting force which opposes drag and propels the airplane is thrust. The same physical principles involved in the generation of lift apply when describing the force of thrust. The thrust necessary to overcome drag and propel the airplane through the air is produced by the power plant turning the propeller. If you look closely at a propeller, you will notice that it looks like a twisted airfoil. As the propeller turns, a lower pressure area is created in front of each rotating blade. The low pressure in front of the propeller, like that above the wing, provides lift which acts forward. This forward-acting lift, or thrust, moves the airplane forward. During unaccelerated flight, where the airplane is neither increasing nor decreasing in airspeed, thrust and drag are equal. However, thrust may be increased by using the throttle to increase power. When you increase power, thrust will exceed drag, causing the airplane to accelerate. With this acceleration, however, there is a corresponding increase in drag. Drag will continue to increase until it is equal to thrust. When these two forces are in equilibrium, the airplane will stop accelerating and maintain the new higher airspeed. The force acting in the opposite direction to thrust is drag. There are 2 types of drag: parasite and induced. Parasite drag includes all the drag not directly related to the production of lift. It is generated by those areas of the airplane which disrupt the otherwise streamlined flow of air. These include items protruding into the airflow, such as the landing gear, rough surfaces, and the mixing of the air, such as where the wing joins the fuselage. As the speed of an airplane increases, the effects of parasite drag also increase. In contrast, induced drag is a direct byproduct of lift. It is greatest at slow speeds with a high angle of attack. Conversely, at higher speeds and at lower angles of attack, induced drag decreases. If the two drag curves are combined and the values added together, we can find a point where drag is at a minimum. This point is known as L over D max, which is where lift, when compared to drag, is at its greatest. In later sections, you will see that flying the airplane at this speed provides the best glide ratio and other performance benefits. The phenomenon known as ground effect occurs when the Earth's surface interferes with normal airflow patterns, thus causing a reduction in induced drag. During flight at altitudes, the downwash created by wingtip vortices causes the average relative wind to be inclined downward. Because lift acts perpendicular to the average relative wind, total lift is inclined aft by the same amount. The component of lift acting in a rearward direction is induced drag. As your airplane descends to within one wingspan of the ground, the wingtip vortices and resulting downwash are deflected horizontally. This in turn moves the average relative wind closer to the horizontal and the total lift vector closer to vertical, thus increasing the vertical component of lift and decreasing induced drag. As a result, the airplane tends to fly longer in ground effect or float down the runway. This can be a problem on shorter runways. Another problem occurs during takeoff, where you may lift off in ground effect at a very slow airspeed. If your airplane hasn't accelerated to a safe climb speed before climbing out of ground effect, the airplane could settle back to the runway. The information presented in this section has provided you with a fundamental knowledge of the forces at work on the airplane during straight and level, unaccelerated flight. The next section will expand your knowledge of what happens to the four basic forces during maneuvering flight. Throughout the years, aircraft engineers have worked to design airplanes which exhibit favorable stability characteristics. Stability can be defined as a design characteristic that causes an airplane to return to steady flight after being disturbed. In any discussion of stability, two kinds must be considered: static and dynamic. Static stability is the initial tendency displayed by an object after it is disturbed from equilibrium. Let's use a marble to demonstrate static stability. When the marble is resting at the bottom, it is in equilibrium. If it is disturbed, its initial tendency is to return to its original position. This tendency is referred to as positive static stability. How an object responds over time, as opposed to its initial reaction, is called dynamic stability. An airplane with both positive static and positive dynamic stability does not immediately return to its original attitude after displacement. Generally, it goes through a series of progressively smaller oscillations. Since an inherently stable platform is highly desirable, a training aircraft is normally designed to exhibit both positive static and dynamic stability. To understand how this is accomplished, we must look at stability in relation to the center of gravity and three axes of flight. Since an aircraft operates in a three-dimensional environment, aircraft movement takes place around one or more of the three axes of rotation. They are called the longitudinal, lateral, and vertical axes of flight. The common reference point for the three axes is the airplane's center of gravity, or CG, which is the theoretical point where the entire weight of the airplane is considered to be concentrated. Since all three axes pass through this point, you can say that the airplane always moves about its CG, regardless of which axis is involved. The ailerons, elevators, and rudder create aerodynamic forces which cause the airplane to rotate about the three axes. When an airplane is banked, it rolls about the longitudinal axis. For a right bank, you rotate the control wheel to the right. This moves the left aileron down and the right aileron up. A closer look at the outboard section of the left wing reveals that as the left aileron moves down, the angle of attack and the camber increase. This produces more lift on the left wing. Conversely, as the right aileron moves up, the angle of attack and the camber decrease, which produces less lift. This difference in lift between the left and right wings causes the airplane to roll about the longitudinal axis. This roll will continue until you return the control wheel to the neutral position. At this time, the lift created by the wings will again be balanced. The airplane will remain in a banked attitude until you move the control wheel to the left. This reverses the process and creates a roll back toward wings level. Moving the control wheel fore and aft moves the elevator or stabilator and creates a pitching movement around the lateral axis. When the control wheel is moved forward, an upward force is created on the elevator, which pitches the nose down. Moving the control wheel aft will create a downward force on the elevator, which in turn will cause the nose of the aircraft to pitch up. The swinging movement of the nose to the left and right is called yaw and occurs about the vertical axis. This rotation is controlled by the rudder. When you step on the right rudder pedal, for instance, the rudder deflects to the right, which creates an aerodynamic force to the left. This causes the nose of the airplane to yaw to the right. Keep in mind that the rudder is not used to turn an airplane in flight. Its primary function is to align the fuselage with the direction of flight. Now let's look at stability about the lateral axis, which is called longitudinal stability. Longitudinal stability is normally obtained by locating the center of gravity ahead of the center of pressure, which is the point along the wing chord where lift is concentrated. This creates a slight nose-heavy condition. To balance this condition, a tail-down or nose-up force is created by installing the horizontal stabilizer with a slightly negative angle of attack. If your airplane pitches up because of a gust of wind or momentary control deflection, the horizontal tail surface moves toward a neutral or slightly positive angle of attack. This decreases the tail-down force, and because the nose-heavy condition is no longer balanced, the nose will return to the trimmed condition. Similarly, if the airplane pitches nose down, the negative angle of attack, and in turn, the tail-down force increases. This tends to return the airplane toward its trimmed attitude. Additional downward forces are imposed on the horizontal surfaces by the downwash created by the propeller and wings. This means that as you reduce power, the tail-down force decreases, allowing the nose to pitch down. Conversely, when you add power, the tail-down force increases and the nose tends to pitch up. Although a certain amount of pitch change with an increase or decrease in power is considered desirable, too much change would unnecessarily increase pilot workload. To help compensate for this, aircraft designers frequently raise the engine thrust line slightly above the center of gravity. This creates a nose-down pitching force when power is added and somewhat offsets the increase in tail-down force caused by additional downwash. Since pitch stability depends upon the difference in location between the center of gravity and the center of lift, the CG's location obviously plays an important role in how an airplane handles. By paying close attention to where and how much fuel, cargo, and people you load on an airplane, you can ensure that the center of gravity will remain within the limits set by the manufacturer. If too much weight is loaded in the front section of the airplane, the CG will be forward of the limit, making the airplane nose-heavy. If this happens, there may not be enough elevator or stabilator force available to rotate the airplane for takeoff, or to raise the nose of the airplane during the landing flare. A potentially worse situation occurs when an airplane is loaded with the CG aft of the approved range. In this case, the airplane will be very unstable in pitch. Even with full forward pressure on the control wheel, recovery from a stall might not be possible. Stability about the longitudinal axes is called lateral stability. Positive lateral stability is the tendency of an airplane to roll back toward a wings level attitude following displacement by a gust of wind or inadvertent control movement. The most common design feature used to attain positive lateral stability is wing dihedral, which is the upward angle of the wings with respect to the horizontal. When an airplane with wing dihedral is displaced in a roll, it will immediately begin to slip in the direction of the lower wing. This creates a higher angle of attack on the low wing, which in turn increases the lift on that wing, resulting in a tendency to roll the airplane back toward wings level. Stability about the yaw axis is referred to as directional stability. When an airplane yaws to the right or left, the large surface area that is behind the center of gravity acts like a big weather vane. This forces the nose of the airplane back toward the original position. So far, we have examined stability with respect to the axes of the airplane. Now let's take a look at some factors relating to the recovery from stalls and spins. It is important to remember that an airplane can stall at any attitude and any airspeed. However, there are other factors which can affect stall speed, such as weight and environmental conditions. As aircraft weight increases, more lift must be produced to support the increased weight. In order to maintain the same airspeed, a higher angle of attack is required to produce the lift necessary to support the increased weight, which in turn causes an increase in the aircraft's stall speed. How you distribute the weight also can have a significant impact on stall speed. For example, a forward CG shifts the balance of the airplane, causing a nose-heavy condition. To counteract this and balance the airplane, tail downforce must be increased. You can do this by increasing the angle of attack, which causes an increase in tail downforce, as well as a corresponding increase in lift and stall speed. Environmental factors such as snow, ice, or frost, which have accumulated on the surface of the wings, can also cause an increase in stall speed by altering the shape of the wing and disrupting the airflow over the wing. The additional weight and drag also causes an increase in the stall speed. Another environmental factor that can affect stall speed is turbulence. The rapid vertical gusts associated with turbulence can cause abrupt changes in the direction of the relative wind and can result in an increase in the angle of attack. Regardless of what causes a stall, you should be able to recognize the indications of an impending stall and take appropriate action to initiate a recovery before it occurs. Most modern airplanes are equipped with a stall warning device, which gives you a warning a few knots before a stall occurs. As the stall approaches, the flight controls will feel mushy. Just before the stall occurs, you will feel a buffeting or vibration. In addition, you may notice a pitching motion as well as a sensation of decreasing airspeed or a sinking feeling. To recover from a stall, lower the nose toward the horizon to decrease the angle of attack and regain lift. Simultaneously, smoothly apply maximum allowable power to minimize altitude loss and increase airspeed. As the airspeed recovers, you should maintain coordinated flight while adjusting power to a normal level. Keep in mind, the reason you practice stalls is not to become proficient at stalling the airplane. Rather, it is to learn to recognize the signs of an impending stall and recover before the airplane reaches a fully stalled condition. The characteristic corkscrew flight path results from an uncoordinated stall where the aircraft's wings are unequally stalled. The three phases of a spin are incipient, fully developed, and recovery. The incipient spin is the portion of the stall when rotation begins, to the moment when the spin has stabilized and the flight path is nearly vertical. At this point, the spin is fully developed. The final phase is spin recovery. To initiate the recovery, retard the throttle and neutralize the ailerons. Then reference your turn coordinator to determine the direction of rotation and apply full rudder opposite the direction of the turn. Now you should briskly move the yoke forward to approximately the neutral position. Depending on the airplane, you may need to move the yoke to a full forward position. As the rotation stops, neutralize the rudder and gradually apply back pressure to return to level flight. During the recovery, you should pay close attention to your aircraft's airspeed and load limits. It's important to understand that as an applicant for a private pilot certificate, you are not required to demonstrate flight proficiency in spin entries or spin recovery techniques. The emphasis in spin training is to provide you with an awareness of the conditions that could lead to an unintentional spin, as well as the general recovery procedures.
Although aircraft may differ in design and performance, the aerodynamic forces acting on any maneuvering aircraft are basically the same. An understanding of the aerodynamics of maneuvering flight will help you develop the skill to perform precise maneuvers while operating your airplane within its design limitations. In straight and level unaccelerated flight, the forces acting on your airplane are in equilibrium. In a stabilized climb, the forces are also in equilibrium. However, the relationship between these forces is changed. When pitch is increased and the flight path is inclined, the force of weight is divided into two components. One component of weight opposes lift 90 degrees to the flight path, and another component acts in the same direction as drag, opposing thrust. Thrust also is divided into separate components, one which acts parallel to the flight path and the other which acts perpendicular to the flight path. The total thrust required is greater in a climb than in straight and level flight. Unless thrust is increased through an addition of power, airspeed will decrease as the pitch attitude increases. To maintain the airspeed, the transition from level flight to a climb normally requires a change in both pitch and power. Once pitch attitude is established and power is properly set, the airspeed and rate of climb will stabilize. During high-power, low-airspeed flight conditions, such as those present in a climb after takeoff, several forces can act to create a noticeable left-turning tendency in propeller-driven aircraft. One of the forces, known as torque, is simply Newton's third law at work. For every action, there is an equal and opposite reaction. The force required to spin a propeller clockwise, as viewed from the cockpit, acts on the rest of the airframe as a force in the opposite direction. In other words, the airframe will rotate counterclockwise or to the left about the longitudinal axis. Gyroscopic precession also causes a left-turning tendency. The aircraft's propeller exhibits the same characteristics as a gyroscope: rigidity in space and precession. Precession produces a left-turning tendency and is most noticeable when the nose is pitched down, such as when a conventional gear aircraft raises its tail wheel during the takeoff roll. As the nose of the aircraft pitches down, a force is applied to the top of the propeller arc. This results in a force exerted 90 degrees in the direction of the propeller's rotation and causes the aircraft to yaw to the left. Another left-turning tendency, known as asymmetrical thrust, or P factor, is most pronounced when the engine is operating at a high power setting and the airplane is flown at a high angle of attack. When the propeller's plane of rotation is perpendicular to the relative wind, the ascending and descending propeller blades have equal angles of attack and produce equal amounts of thrust. As the airplane pitches to a high angle of attack, the descending blade of the propeller has a higher angle of attack than the ascending blade. The result is that more thrust is produced by the descending blade on the right side of the airplane, causing a turn to the left. Spiraling slipstream, which also produces a left-turning tendency, is the result of the airflow behind the propeller moving rearward in a corkscrew motion around the fuselage. Since the propeller is rotating clockwise, the slipstream pushes the vertical stabilizer to the right, causing the nose of the airplane to yaw left. To help counteract left-turning tendency and make the airplane easier to control, some manufacturers have incorporated special design features. One such feature is a small metal tab positioned on the trailing edge of the rudder. The tab is bent slightly to the left, so the pressure of the passing airflow pushes on the tab, forcing the rudder to the right. This creates a yawing moment, which counteracts the airplane's tendency to turn left. In stabilized descending flight, like a stabilized climb, the aerodynamic forces acting on the airplane are in equilibrium. However, during a descent, one component of weight acts perpendicular to the flight path, opposing lift, while the other acts forward along the flight path, adding to thrust and opposing drag. If the power setting is unchanged, airspeed increases as the nose is lowered in a descent, and a corresponding increase in parasite drag works to balance the force of weight. When airspeed stabilizes, aerodynamic forces are again in equilibrium. If the force of thrust is removed by reducing the power to idle, the forward component of weight must be increased to counteract the force of drag. In order to maintain the same airspeed, the nose must be lowered even further. In a gliding descent, the best glide angle and the best glide distance result from flying the airplane at an angle of attack which provides the least amount of total drag for the corresponding lift. This angle of attack is referred to as the maximum lift-to-drag ratio, or LD max. The aircraft's best glide speed normally is achieved at the angle of attack corresponding to LD max. The best glide speed is published in the pilot's operating handbook. For example, the best glide speed for this airplane at 2,600 pounds is 75 knots with the propeller windmilling, flaps and gear up in calm wind conditions. Glide ratio represents the distance an airplane will travel forward without power in relation to altitude loss. For example, a glide ratio of 10:1 means an airplane will travel approximately 10,000 feet of horizontal distance for every 1,000 feet of altitude lost in a descent. The angle between the flight path and the horizon is called the glide angle. As drag increases, so does glide angle. For example, in a glide when the landing gear is lowered, there is a corresponding increase in drag. To maintain the same airspeed, this increase in drag is counteracted by lowering the nose of the airplane, thus increasing the glide angle, which results in a reduced glide distance. Although the weight of the airplane doesn't affect glide ratio, it does affect the airspeed that must be flown to attain the best glide distance. Since a heavier airplane will sink faster, a higher airspeed must be maintained to support the greater weight and yield the same glide distance as a lighter airplane. Turning flight introduces new concepts with respect to the aerodynamic forces acting on the airplane. In a bank, total lift is divided into two components. One acts vertically to oppose weight, and the other acts horizontally to move the airplane in the direction of the turn. Since the vertical component of lift is reduced in a turn, to maintain altitude, you must apply back pressure on the yoke to increase the angle of attack until the vertical components of lift and weight are again equal. The horizontal component of lift creates centripetal force, which acts toward the center of rotation. During the turn, this center-seeking force works to oppose inertia, which is the tendency of the airplane to continue in a straight line. As the airplane enters a turn, the aileron on the inside of the turn is raised, and the aileron on the outside of the turn is lowered. The lowered aileron increases the angle of attack and produces more lift for that wing. Since induced drag is a byproduct of lift, the outside wing also produces more drag. This increase in drag causes a yawing tendency toward the outside of the turn known as adverse yaw. When you enter a turn, you should depress the rudder in the same direction of the turn to help compensate for adverse yaw. Once you are established in the turn, you may neutralize the ailerons to prevent further roll. Since the cause of adverse yaw is removed, rudder pressure also can be relaxed. When you roll out of the turn, you should apply coordinated aileron and rudder pressure in the opposite direction of the turn to return to a wings level attitude. During a turn, the outside wing travels faster than the inside wing and creates more lift, which may cause the airplane to continue rolling beyond the desired bank angle. You can correct this overbanking tendency by applying a small amount of aileron in the opposite direction of the turn. Two terms which are used to define the performance of an airplane in turning flight are rate of turn and radius of turn. Rate of turn is the amount of time for an airplane to turn a specified number of degrees. Every aircraft will turn at the same rate when flown at the same airspeed and angle of bank. If airspeed is increased and the angle of bank remains the same, the rate of turn will decrease. Conversely, a constant airspeed with an increased angle of bank will result in a faster rate of turn. The radius of turn, or the distance an aircraft must be flown to complete a turn, is also dependent on airspeed and angle of bank. For example, when airspeed is increased and the angle of bank remains the same, the radius of turn increases. However, if the airspeed remains the same and angle of bank is increased, the radius of turn is smaller. Load factor is the ratio of the load supported by the wings to the actual weight of the airplane. An airplane in straight and level unaccelerated flight has a load factor of 1, which means the wings are supporting only the actual weight of the airplane and its contents. You may be more familiar with the term G-force, which is used to describe loads imposed on a maneuvering aircraft. You can relate G-force to the feeling you get while riding a roller coaster. As you enter a bank turn on a roller coaster, you feel the forces created by the combination of centripetal force and inertia as seat pressure. The pressure you feel is, in reality, an increase in load factor that is expressed in Gs. As the roller coaster reaches the top of the track and begins a rapid descent, you may feel a sensation of weightlessness if centripetal force and inertia cancel each other out. It's important to note that a change in load factor can occur at any time due to pilot control input or environmental conditions such as turbulence. The amount of stress which an airplane can withstand before structural damage or failure occurs is called the limit load factor. Most general aviation aircraft are certificated in one of 3 categories: normal, utility, or acrobatic. Many general aviation airplanes are certificated in the normal category, with a limit load factor of 3.8 positive Gs and 1.52 negative Gs, which is sufficient for basic training maneuvers. Airplanes which are certificated in the utility category have a limit load factor of 4.4 positive Gs and 1.76 negative Gs. Acrobatic airplanes are even less restricted, with a limit load factor of 6 positive Gs and 3 negative Gs. Regardless of the category, it's very important to adhere to proper loading techniques and always fly within the limits listed in the pilot's operating handbook. Another way to avoid possible damage to your airplane by excess loads is to observe the design maneuvering airspeed, or VA. Related to stall speed, this is the maximum speed at which you can use full or abrupt control movements without overstressing the airframe. VA is normally not marked on the airspeed indicator since it varies with total weight. Maneuvering speed decreases with a decrease in weight because an airplane operating at a lighter weight is subject to more rapid acceleration from gusts and turbulence. If G loading increases while operating below maneuvering speed, your airplane will stall before the limit load factor is exceeded, thus avoiding potential damage to the airplane. Understanding the forces acting on your airplane will improve your ability to perform more complex maneuvers with greater accuracy and safety as you progress through your flight training.